All right, this is our ninth set of notes from Chapter 8 on the graphical representation of the phase behavior of mixtures. More specifically, this is our third set of notes on graphical representation of LLE. And so when we first talked about LLE, we kind of motivated it as, LLE is going to be important for the design of extraction processes. Okay, and the example I started with is, if I have, say, a protein dissolved in a solvent that I want to try and get a solution that's more concentrated in that protein, I can contact it with another solvent, where that other solvent essentially has a high affinity for the solute, but doesn't really like that original solvent much, where the goal would be to preferentially suck up the solute out of solution and concentrate it in this other solvent, okay, for lack of a better description. Okay, and the basic sort of extraction process is called a mixer settler, where I take my solvent with my solute in it, I mix it with my other solvent that I hope to preferentially suck up the solute, right? I mix the heck out of them. Why I mix the heck out of them is, well, if I just had two liquids that are sitting on top of each other, right, my diffusion is going to be rather slow in that liquid phase compared to, say, a vapor phase. And so if I were just to contact those two liquids, right, the time it takes for my solute to come out of solvent 1 to go into solvent 2 is going to be relatively slow, right? Remember, thermodynamics is just cared about properties in the infinite time limit. What happens after those two solvents have just sat on top of each other for a long enough time so that they reach equilibrium, right? And by equilibrium, in this case, it'd be distribution of those, the concentration of those components in all my phases, right? So I mix the heck out of it to try and speed up the mixing process, to try and minimize any of these mass transfer limitations. Then by settler, right? Then I'm going to allow my system to settle. So I pull out two solvents out the top and bottom, say, of my flash drum. Okay? And in terms of designing mixer settlers, what is key is the ability just to read ternary phase diagram. Okay, and so that's what we're going to take a look at in this set of notes. All right, so here's an example of a ternary phase diagram, so a Gibbs triangle. Okay, and in terms of nomenclature, all right, we're going to have an extract phase in equilibrium with a raffinate phase. Okay, so my extract phase is going to contain my solute and diluent in a solvent, and my raffinate phase is going to contain my solvent or solute and solvent and diluent. Okay, and so what does this mean, right? So originally, I'm going to have my solute is going to be dissolved in my diluent, right? So initially, I have a solute dissolved in my diluent. And then what I'm going to do is I'm going to take that mixture and I'm going to contact it with my solvent that I hope to preferentially suck up my solute with, okay? So my solvent is what I'm adding to try and preferentially suck up my solute, okay? So my extract phase will contain my solute and diluent in my solvent. Okay, so your extract phase should ideally contain mostly solvent and solute with only a tiny little diluent. It's just, we say it wants to preferentially suck up my solute. The selectivity for just the solute, may not necessarily be 1 and typically isn't just 1. My raffinate phase is going to be my phase that's left behind, which is mostly diluent, but still contains some solute, the solute not sucked up, and a little solvent, that solvent being what I added to try and suck up my solute, right? And why we have all three components at the end in both phases, we'll talk about. Okay, but you can think of your extract phase kind of being the stream coming out of my drum, which contains hopefully my concentrated solute, or you can think of it as, say, my product type of stream. Okay. So these raffinating and extract, if I think of this as a flash drum, I have mixture going in, then I have an extract and raffinate phase coming out that are in equilibrium with each other. Okay, so if I think about graphing this, so if I have a ternary system, so three components, so I have a ternary system, and if my system's in two-phase equilibria, where I have two liquid phases, how many degrees of freedom do I have? Well, F is equal to n minus pi plus 2. So if I have n is 3 components, in two phases plus 2, I have 3 degrees of freedom. Okay, so at liquid-liquid equilibrium, for my ternary system, I have 3 degrees of freedom. And if I think about the case of a ternary system in a single phase, well, n is 3, number of phases is 1, so plus 2, I have 4 degrees of freedom. So if I wanted to attempt to plot the properties of my ternary system in a 2-dimensional phase diagram, I would need to fix 2 degrees of freedom. Okay, this is different to when we had txy and pxy phase diagrams, in which I just specified t or p to allow me to plot in 2Ds. Okay, here I have 4 degrees of freedom, so in order to plot in 2 dimensions, in order to reduce this down to 2 degrees of freedom or 2 variables, I need to fix 2 properties. And so my ternary phase diagram, for this reason, temperature and pressure are going to be fixed. So in a ternary phase diagram, temperature and pressure are fixed throughout the diagram. And then, the diagram looks just a little different than, normal graph paper, right? And why it looks a little different is when I think about my binary system, in terms of mole fractions, I know my mole fractions have to sum to 1. So if I just have a binary system, x2 is just 1 minus x1. Right? So I can just plot things with respect to, say, x1 and y1, because if I wanted x2, it's just 1 minus that. When it comes to a ternary system, things change a little bit. Right? We still have that my mole fractions sum to 1, but now it's, say x1 plus x2 plus x3 is equal to 1. So if I know, say, the value of x1, that's not enough to get x2 and x3, right? I would need to know x1 and x2 in order to back out x3. Okay? And so we'll talk about how to read this, but the origin of plotting this in this triangular fashion is just so that we could represent all 3 compositions. All right. So in terms of interpreting this phase diagram, so this particular case, our solute, right, is going to be labeled A, acetone, okay, here, okay. Our diluent is B, water, okay. And so essentially we originally have acetone dissolved in water, okay. We're going to try and extract acetone from water by contacting it with our solvent, S, which is MIK, methyl isobutyl ketone. Okay, so here's my solvent down here. All right, so in terms of being able to read this animal, okay, so we have a ternary mixture of acetone, MIK, and water. Okay, so acetone is up here, here's MIK, and here's water. Okay, now how do we read this? So if I look at the sides of my triangle, this side's labeled mass fraction acetone, we have mass fraction water, and mass fraction MIK. So here we're using mass fractions. They're the same essentially as mole fractions. Mole fractions, moles of component I divided by total. This is mass of component I divided by total, right? And so this diagram would look essentially the same if we were to use mass fractions. Okay. All right. So here's acetone, right? And if I look at this acetone point, it says 1, right? So this point right here, this top point of my triangle, would correspond to a system of pure acetone. Okay. Now what I'm doing is if I look along this left side where it says mass fraction acetone, it's counting down from 1 to 0.1 all the way to the 0, right? And we'll get to what that means in terms of 0. If I want to read off the concentration of acetone, I'm looking at the lines that are parallel to that point. Okay? And so, this line, right, then crosses my essentially left axis at 0.9. That would correspond to 0.9 mole fractions acetone, 0.9 or 0.85, 0.8, 0.75, 0.7, and so on and so forth, all the way. So here's 0.1. This would be 0.05, all the way till I get to 0. All right, so where it says 1 MIK and 1 water, that would correspond to 0 acetone. All right, so next, if I want to look at concentrations of MIK, so I look at this corner, all right, so this corner, this point would correspond to a system of pure MIK. If I want to read off compositions of MIK, I'm again looking at the lines that are parallel to this point, okay, and where I read off my MIK mole fractions is, well, this bottom axis is labeled mass fraction MIK, okay, so this is pure MIK, so 1. Okay, this line hits this axis at 0.9. That's 0.9 mass fractions MIK, and so on and so forth. So this would be 0.3 mass fractions MIK, all the way down to 0. All right, and they could do the same thing for water. Okay, I'm reading off the lines that are parallel to that point. Here's pure water. All right, I read off the water concentrations from that axis. Okay, so if I want to locate a mixture that's 70% acetone, 20% MIK, and 10% water, so this sums up to 100%. All right, I could first find acetone. So I'd go to my acetone axis, find 0.7, right, and draw a line across on that horizontal line. I could find 20% MIK. So here's my MIK axis. So find it, and then I draw a line across on the line parallel to the MIK corner, right? And essentially where they cross, right, the cross marks the spot, right? So once I know two mole fractions or mass fractions, I know the third because I have to sum to 1. But if I were to plot that 10% water line, I could. All right, here's 10% water. Draw the line, right, that's parallel to that corner, right, and all three cross at the same spot, right? And so, this mixture would be right here on this phase diagram. In theory, once I specify 2 of the mass fractions, the third is fixed. So I need only 2 of the compositions, but I could just as well plot all 3. All right. So now if you look a little further. If I look at this left axis here, okay, where it says mass fraction acetone, okay, down in this bottom corner, right, this is pure MIK, right, that's 100% MIK. Up here we have pure acetone, okay. So if I look at just this axis then, okay, this would correspond to a mixture of pure MIK and pure acetone, going from pure acetone to pure MIK. Okay, so it's a binary mixture of acetone and MIK. Look at the bottom axis, MIK and water. This would correspond to a binary mixture of MIK and water. And if I look at my other side, between acetone and water, this would correspond to a binary mixture of acetone and water. Okay, cool. All right, so those axes correspond to binary mixtures, within the area of my triangle. So underneath those axes, right, this corresponds to a ternary mixture. Okay. So I have my phase envelope within this ternary system. Okay, and underneath the phase envelope, I have a 2-phase mixture. Okay, so beneath the dome, I have a 2-phase mixture. And so, the curve now I correspond to my miscibility boundary. Okay, and why I call it my miscibility boundary is above my dome, I have a single phase. Okay, so this is going to be the boundary separating single phase from 2-phase. Okay. 2-phase, I have 2 partially miscible liquids, so I'm going to end up with 2 liquid phases. Up here, I have a single phase, right? So miscibility, in which I go from being miscible to partially miscible. All right, so again, here's my ternary system. If I specify an acetone, MIK, and water concentration, and it puts me underneath this dome, right? Underneath the dome, I have a 2-phase system. Okay. Now the question comes in, well, if I'm in my 2-phase system, I know that those 2 liquids, I'm going to phase split to form 2 liquids, and at equilibrium, I know that I'm going to have an equality of temperatures and pressure in those 2 phases. Okay, so when we had our TXY and PXY phase diagrams, I just either drew an isobar or an isotherm, right, and life was good. We can't exactly do the same thing here, right? And the reason I can't is if you recall all the way back to the beginning of the set of slides, is temperature and pressure is held fixed or is constant throughout this entire diagram. All right, so in terms of drawing isotherms or isobars, well, temperature and pressure are already uniform throughout. Okay, so instead, what we need to have on our phase diagram are called tie lines. Okay, so you'll see a bunch of these lines drawn that connect the 2 sides of my miscibility boundary or my phase envelope. Okay, so these are called tie lines, and those are experimentally determined. Okay, and so if I'm in the 2-phase region, I'm going to get phase splitting along a tie line. Okay, so now the challenge is tie lines, right? They're not just isotherms or isobars. These are things that would have to be determined experimentally, right? And so what I would do, or what the experiment would look like, is if I had a mixture that was, so mixtures all along, this line, and I were to do a shake flask experiment. So I take that mixture, I shake it up, and then I let it settle, and then I extract, the top phase from the bottom and measure the composition in those 2 phases. All right, that would give me the composition of, these 2 points. All right, and so if I did that at enough intermediate compositions, all right, I could use that to construct a series of tie lines. And so, the important point is that these tie lines all have to be experimentally determined and available on your graph. If you have a composition that doesn't fall exactly on a tie line, well, then you can interpolate. Or if I had an excess Gibbs free energy model parameterized for my system, I could essentially just directly calculate the tie line and plot it on there. But what's important is these aren't just isotherms or isobars, because temperature and pressure are constant throughout. So if I get phase splitting, how I get the composition of those two phases is by one of these tie lines. Okay, cool. Okay, so if I look at my tie lines, right, so as I increase my acetone concentration, in this case, the tie lines become skinnier and skinnier all the way until I reach the point of my miscibility boundary, and we call that point my plate point. So beyond my plate point, essentially no separation is possible, right? That for acetone concentrations greater than this, I'm going to be in a single phase, right? And when I say acetone, remember that's my solute. I read off concentrations from these horizontal lines here. So as long as I have an acetone concentration, say greater than 0.5, then I'm going to have a single phase. Okay, so my plate point, beyond that, no separation is possible. Okay. All right, so if I look at my binary axes again, so if I look at the left one, this is my mixture of acetone and MiK. Okay, so it doesn't cross my phase boundary at all. So we'd say acetone and MiK are completely miscible. This is my solute and my solvent. If I look at acetone and water, right, phase boundary doesn't cross that at all. So we say acetone and water are completely miscible. All right, that's acetone, and this is my initial diluent. It's what's initially dissolved in. But if I look at the bottom axis now, okay, so this is a binary mixture of MiK and water. My phase envelope touches here and here. Okay, what that tells us is that MiK and water are partially miscible. So if I had a mixture that was say 0.5 mass fracs water, right, it'd be right here, right on this bottom axis. This tells me I'm going to get phase splitting, and here my plate point is just my bottom axis, where I'd have a liquid of this concentration, which is almost pure MiK, in the equilibrium with a mixture of this concentration, which is essentially virtually pure water. All right, so MiK and water are partially miscible, right? In this case, they're virtually immiscible, right? And essentially, I want a diluent and a solvent that really don't like each other, right? I just want that solvent to really like the solute, but not like the diluent, right? And that's what I have here, right? So these are partially miscible, and so I'm going to get phase splitting to form two liquid phases, which are essentially pure water and pure MiK. Okay. So where these become challenging, though, is what happens as the concentration of acetone increases. Okay. So the challenge is, okay, we have MiK and water which hate each other. So my solvent doesn't like my diluent. But as we just saw, both MiK and water are miscible with acetone. They both like acetone. And so what happens is, if I have a bunch of acetone in my diluent water, okay, well, MiK hates water, it likes acetone. And so what happens is, if I have a mixture of water and acetone, right, that liquid is much more, favorable or attractive to MiK than, the case of pure water. Okay, and so what happens is, when I have this high acetone concentration, I end up creating a solvent or a liquid for which it's favorable for MiK to be present there. Okay, and if I were to look at this graphically, so I have a mixture, say 50% MiK and water. So again, we get phase splitting along this tie line, this bottom axis, and essentially I get two liquid phases that are virtually pure MiK and pure water. Okay, now what happens is we add acetone dropwise. Well, if I add acetone, right, in the limit that I add a ton of acetone, MiK and water will essentially be diluted, and I would reach the state of pure acetone. So I'm just going to draw a line going from this original binary mixture that I started with to the limit of pure acetone, the limit that I've added a ton. Okay, and so if I march up this, okay, so as I move up, but stay in the two-phase region, I'm going to get separation along a tie line. Okay, what you'll find is the tie lines become shorter and shorter, right? And so, down here, I have an extract phase, so an MiK-rich phase. So if I'm, right here, so M read off MiK here, right? So it'll have, say, 0.75 mole fractions MiK. In terms of acetone, it'll be about 0.2 mole fractions acetone, so that means just 0.05 mass fractions water, right? So I get a lot of high concentration of acetone in that MIK, but very little water. Okay. What happens though is as the concentration of acetone increases, right, my tie line becomes shorter and shorter, and I begin to increase the concentration of water in that extract phase, right? So I not only suck up acetone, but now I'm going to suck up water. Okay, and so up here, okay, so now my mole fraction of water is up to 0.5 mole fracs. Okay, so this is problematic. Okay, so the issue is as I have more and more acetone in that system, I'm going to continue to get more and more water then in my extract phase, in my MIK-rich phase, because by having acetone present, right, those two solvents which naturally hate each other are going to begin to like each other more because they have that common component that they like, present in higher numbers in both systems, right? And that goes all the way to once I get to 0.5 mole fractions of MIK, right? Separation is no longer possible. You're just going to get two completely miscible phases. Okay, and so that's reading, that type 1 ternary LLE phase diagram. So this is just a picture taken from Decama's LLE collection. And all this has meant is, we looked at type 1. There are other types available. We won't get into all of them, but, same essentially principles in terms of analyzing them exist. So we looked at a type 1 system here. Here's a type 0. Type 0 is kind of cool, where all three components are actually completely miscible with each other, but you have some intermediate composition in which you get two-phase equilibrium. Type 2 is kind of cool, so component 1 and 2 are completely miscible, but 2 and 3 and 1 and 3 are both partially miscible. Okay, so my solute would only be partially miscible with one of the solvents, okay, and you get other crazy types of behavior. Okay, but that's it for the notes, and yeah.